In this video, let's take a look at solving absolute value functions. We'll look at two cases, one where we're asked to solve an equality and one where we're asked to solve an inequality. So to start with, let's look at our equality. Say we're given two functions, f of x equals 2 times the absolute value of x minus 4 plus 1, and g of x equals x. And we want to know when f of x equals g of x. In this case, g of x might just be a number. It might be 2 or 4 or 8. In our example, g of x is x, right? It's a line as if it was y equals x, rather than just a number. Either way, we're going to solve it the same way. We end up with 2x minus 4 plus 1 equals x. Our first step is to isolate our absolute value. So we can subtract 1 from both sides, and we'll end up with 2 times the absolute value of x minus 4 equals x minus 1, and then divide everything by 2. So we get x minus 4 equals x minus 1 over 2. At this point, let's remember something. If we have the absolute value of x equals 3, what that means is that x is 3 units away from 0. So let's picture this on a number line. So here's our number line. If this is 0, there's 1, 2, 3, 4, negative 1, 2, 3, 4. What this means is that x is either 3 units this way, right? And so we're at 3, or it's 3 units in the other direction, 1, 2, 3. Either way, we're 3 units away from 0. That's really what we're saying here. So x might be 3, or it might be negative 3. So here, to find our solution, we have to apply the same principle. What we'll get is, instead of just x, we have an x minus 4. So x minus 4 equals this term over here, as it was the x equals 3. So x minus 4 equals x minus 1 over 2. And we need the other case as well, where we have our x minus 4 equals the negative of what was on this side of the equality. So the negative of x minus 1 over 2. And that negative applies to everything. So we can solve these one at a time. First, let's multiply everything by 2 to get rid of these fractions. So we'll have 2x minus 8 equals x minus 1. If we subtract x from both sides, we get x minus 8 equals negative 1. And then we'll add 8 to both sides, and we'll get x equals 7. So that's one case, x equals 7. The other case over here is x minus 4 equals negative x minus 1 over 2. Again, let's multiply everything by 2. So we have 2x minus 8 equals negative x minus 1. Let's take this negative all the way through in our next step. 2x minus 8 equals negative x plus 1. We can add x to both sides, so we get 3x minus 8 equals 1. We'll add 8 to both sides, so we get 3x equals 9. Divide everything by 3, and we get x equals 3. So we have two cases here, and we need to check for extraneous answers. Remember, an absolute value function is made up of two rays that terminate at the vertex. If those rays did not terminate at the vertex and kept going, sometimes we get that solution instead. So where, for example, x might cross the ray that doesn't actually exist in our absolute value function, but could exist if it was considered a solid line. Let me draw you a quick picture of what that might look like. So if we have our absolute value function, right, here's where these lines continue on, right? This line continues on here, this line continues on here, but the dotted parts are not part of our absolute value function. So sometimes we might get, if this was the function we were interested in, we might get this is a solution and this is a solution, and this is not actually a solution because it's not crossing our absolute value function. That's what I mean by extraneous answers. So to check for extraneous answers, we take our two values, x equals 7 and x equals 3, plug them back into our original equation, f of x equals g of x, and see if we get a correct statement at the end. So if we're checking, we would get 2 times the absolute value of x minus 4 plus 1 equals x. Let's check x equals 7 first. We end up with 2 times 7 minus 4 plus 1 equals 7. 2 times 7 minus 4 is 3, plus 1 equals 7. 2 times the absolute value of 3 is 2 times 3, which is 6, plus 1 equals 7, and we get 7 equals 7. So we know then that this is in fact a solution. Let's check our answer, x equals 3. 2 times the absolute value of x minus 4 plus 1 equals x. We'll substitute 3 in for x. 2 times 3 minus 4 plus 1 equals 3. 3 minus 4 is a negative 1, so we get 2 times the absolute value of negative 1 plus 1 equals 3. The absolute value of a negative 1 is 1, so this ends up being 2 plus 1 equals 3. 3 equals 3. This is also a correct answer. So in this case, we have two solutions, x equals 7 and x equals 3. Now let's look at an inequality. So we're talking about a greater than or a less than, or a greater than or equal to, or a less than or equal to. So let's solve this inequality. Negative 2 times the absolute value of x minus 4 plus 2 is less than or equal to 4x. The same principles apply. We want to isolate this absolute value and then take the positive and the negative. There's one thing to notice when we're taking the positive and negative. So let's isolate our absolute value first. If we subtract 2 from both sides, we get negative 2 times the absolute value of x minus 4 is less than or equal to 4x minus 2. And then if we divide everything by a negative 2, we get the absolute value of x minus 4 is less than or equal to, because we're dividing by a negative, this becomes a greater than or equal to. 4 divided by a negative 2 is a negative 2x. Negative 2 divided by a negative 2 is 1. So then, let me just rewrite that line. We have x minus 4 is greater than or equal to negative 2x plus 1. Now, just like in our first example, where we had to take the positive and negative of this side, we're going to do the same thing, with one difference. Let's think back to this absolute value of x is 3, and now let's look at the absolute value of x is greater than 3. Let's look at that on a number line. So here's our 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. So what this means is that x has to be more than 3 units away from 0. So here's 1, 2, 3. We'll put a circle around that, and it's anything that's more than that, right? Anything over here is more than 3 units away from 0. Similarly, if we look at our negative 3, put an open circle around that, anything that's more than 3 units away from 0 is now heading in this direction. So x has to be greater than 3, and x can be less than negative 3. So see how this inequality switches here when we switch the sign? In the equals case, we just cared about the positive and negative. Here, when we take the negative, we have to flip our inequality as well. So this was kind of our little note. So when we look at the two cases for this, we'll end up with x minus 4 is greater than or equal to negative 2x plus 1, as our statement is written, and x minus 4 will switch this from a greater than or equal to a less than or equal to, and then we'll take the negative of that side. So negative, and then in brackets, negative 2x plus 1. And we'll distribute this negative all the way through. So now let's solve. If we add 2x to both sides, we'll get 3x minus 4 greater than or equal to 1. If we add 4 to both sides, we'll get 3x greater than or equal to 5. So x is greater than or equal to 5/3. And you could change that into a decimal if you want to. When we solve this case, we'll get, let's distribute that negative first. X minus 4 less than or equal to negative times a negative is a positive. Negative times a positive is a negative. And now we can solve. Let's subtract 2x from both sides. So x minus 2x gives us a negative x minus 4 less than or equal to negative 1. Let's add 4 to both sides. We get negative x less than or equal to 3. And now let's divide everything by a negative 1. We get x, remember, because we're dividing by a negative number, this inequality flips again, greater than or equal to negative 3. So we have two options, and we do need to check them, just like we did in our first example. So let's go up here to check. When we're checking, we're going to switch our inequality to an equality. We'll switch it to an equal sign, because really we want to see where these two functions cross, if they do actually cross. That's what we're checking for. Or are they actually crossing in one of these rays that doesn't actually exist? So we can ignore the greater than or less than, and we can just use an equal sign. So let's check our x's negative 3 first. So if we have negative 2 times x minus 4 plus 2 equals 4x, let's check this one first, where x is negative 3. So negative 2 times negative 3 minus 4 plus 2 equals 4 times negative 3. We get negative 2 times the absolute value of negative 7 plus 2 equals 4 times a negative 3 is a negative 12. The absolute value of negative 7 is 7. 7 times negative 2 is negative 14, plus 2 equals negative 12. Negative 14 plus 2 is negative 12. So we get negative 12 equals negative 12. So that's true. So this is, in fact, one of our answers. Let's check our other case as well. We end up with negative 2. Let's draw a line here just so we can keep them apart a little bit, times the absolute value of 5/3 minus 4 plus 2 equals 4 times 5/3. This becomes negative 2 times the absolute value of, if we do 5/3 minus 4, I'm going to change this into a decimal now. We get negative 2.33 plus 2 equals 4 times 5/3. Again, I'll change that into a decimal. It's 6.67 when I do that multiplication. I'm running out of room a little bit, but I think we can probably squeeze in our answer. The absolute value of negative 2.33 is 2.33. So we'll take 2.33 times a negative 2, and we'll get negative 4.66. We still have this plus 2 equals 6.67. If we add 2 to negative 4.66, we end up with negative 2.66 equals 6.67. This is not true, which means this cannot be one of our solutions. So what we found then is negative 2 times the absolute value of x minus 4 plus 2 is less than or equal to 4x over, we want x to be greater than negative 3, so from negative 3 to positive infinity. And it includes the negative 3 because it's greater than or equal to. Sometimes we'll have one answer like this. Sometimes we'll have a union where there are two different regions of the absolute value function that solve our inequality. Sometimes there won't be any answers. So we really do have to check and then see how this fits with the domain of our function to see what our solution is. I hope that clears things up for you.